It's a great pleasure that we have Sean Oughton for today's seminar. So Sean, in fact, we had a temporal overlap in US doing PhD. So he did his PhD with Bill Matthews in Delaware, and I was in Maryland. So it was some 200-kilometer distance. Then after that, he went to University College London. After that, he went to St. Andrews, University of St. Andrews. Then after that, he moved to New Zealand, University of Waikato. Did I get it right? I hope I did get it right. And
that was good.
He has been, he's a professor in Waikato, and he works. I mean, he's an expert in MHD turbulence. Some of it he's going to tell us today. Also in solar wind and solar physics and so on. Okay, Sean, it's all yours.
Thank you, Mahendra. It's great to have this invitation. So thanks for that. I see life has been less stressful for you. You still have all your hair, despite us being graduate students at the same time and the same age, and mine's all gone. So the topic today is MHD turbulence phenomenologies, and I want to sort of point out an issue with the Iroshnikov and Kraichnan phenomenologies that really relates to some tension between assumptions about isotropy that perhaps shouldn't have been made, and that highlights the importance of the two-dimensional modes in the turbulence there. And this is some work that was done by my student, Alan Lynn, and myself a little while ago. Unfortunately, Alan, although he was a very good student, decided that the commercial world had more to offer than the research world, and he's no longer doing any sort of research, MHD or otherwise. Okay, so just as an introduction, the original phenomenologies for MHD turbulence were by Iroshnikov and Kraichnan, and the models are a bit different. They're not the same. I'll say some more about that later. But crudely, that they both have a strong mean magnetic field, strong meaning that it dominates the energy. There's much more energy in it than there is in the fluctuations. And the fluctuations are mostly Alfvén waves, and with a time scale associated with them that it should be, let's use my mouse here, it should be K dot B naught in here if it's really the frequency of the Alfvén waves. But in these phenomenologies, you forget about the dot and you just pretend it's K times B naught, ignore the cosine theta. So that's an isotropic approximation to the anisotropic time scale. But if you go ahead and do that, then you come up with a prediction for the energy spectrum, E of K, which we're going to see a bit of. It goes like K to the -3/2. Okay, good. What I want to look at and focus on here is how well these assumptions about the isotropy, K times B naught versus K dot B naught, stand up. So that's the sort of overview of what we're going to cover in the next little while here. And then in outline the rest of the talk, we'll look at the Navier-Stokes equation and the Kolmogorov phenomenology just to remind us about the important timescales that are in there. And then look at Kraichnan's approach to turbulence phenomenologies, which is a different one, a physically different one, you might say. And then go on from there to the main part, which is how does this tension between a preferred direction associated with the mean field and assumptions about isotropy, how does that play out? So we'll do some analysis there and then look at some simulations to see how that goes as well. And then if there's a little bit of time left, I'll talk about the solar wind and a related thing from these MHD phenomenologies to do with the Alfvén ratio, how much kinetic energy in the fluctuations versus how much magnetic energy. So just, yeah, the first few sections here about Kolmogorov and Kraichnan are largely review of material that many of you, I guess, will be very familiar with. In fact, I went to a talk the other day where the speaker said, everything's going to be a review, essentially. Anything new in this talk is a typo. Now, I wouldn't go that far for this talk, but there is a bit of review material in this first part here. Okay, so Navier-Stokes equations and using Kolmogorov-Ubikov phenomenologies to get the energy spectrum out of that. There are at least 3 timescales in Navier-Stokes turbulence that are conceptually distinct. They might be numerically the same, but they're conceptually different aspects of the physics. And the ones I'm interested in here are the nonlinear time, the triple correlation timescale, and the spectral transfer timescale. So we'll just say a little bit more about those. So here's the Navier-Stokes equation, or part of it. dV dt is minus v dot grad v, and this red bit here is the part doing the advection, and there's a time scale associated with that, a typical length from the grad, say the correlation length, and a typical speed, maybe the RMS velocity for the flow, gives you the nonlinear time scale. Okay, good. That's sort of a global nonlinear time scale. But if we're more interested in things that are happening at different scales, then we might want to look at things in Fourier space. And then we generalize this. Instead of using the correlation length and the RMS velocity, we use the scale we're interested in, L, and the typical speed at that scale, use subscript L. Okay, so 1 over K is the same as L, our scale, and the typical speed. If we take the energy spectrum, multiplied by K, that gives us a speed squared. So the square root gives us the UL there. Okay, we're going to see that particular formula, which I think you're all familiar with, several times in the talk here. So that's the first conceptual timescale, the nonlinear time. The second one is the triple correlation timescale. So again, in Fourier space, we look at the time evolution of the energy spectrum, E of K, then that's this integral, convolution integral of, okay, there's some K's and things in here, but there's really 3 different velocity modes with different wave vectors. V of Q, Q is one wave vector, V of K minus Q, and V of K. Okay, so 1, 2, 3 velocities. That's a triple correlation, and there's a characteristic time scale associated with its evolution, what we might call tau 3 for triple, tau 3 of K in that case. That's 2 of our time scales. The third one, the spectral transfer time, this tau SP here, where does that come from? Well, if you're interested in this epsilon, the usual turbulence epsilon, which is the rate of energy transfer through the inertial range, then that is roughly speaking, or is modeled as the energy at scale K, K times the spectrum, divided by that spectral time scale. Okay. So 3 time scales, nonlinear, triple correlation, and spectral transfer. If you really had isotropic Navier-Stokes, which you often do, there are plenty of situations where that's the case, then you might argue that, yes, they're different conceptually, but numerically, in terms of their value, you'd expect them all to be about the same. And that seems a good and reasonable assumption there. So using this formula up here for the nonlinear time, they would all be about 1 over K, square root of K, times the spectrum. Okay. You don't need all of that to do the Kolmogorov, to get the Kolmogorov spectrum for Navier-Stokes, but we're going to be using it in the MHD case. Sticking with the Navier-Stokes though, for a minute, we use the Kolmogorov-Ubikov approach. So here's the energy spectrum on the vertical and the wave numbers on the horizontal. Some sort of spectrum here in blue. If we choose a particular value of K, then epsilon is the energy transfer rate is equivalent to the net energy that comes from values of K below this line to values to K values that are above that line. Okay. So what did Kolmogorov and Ubikov do? Statistically steady turbulence was the assumption with a large Reynolds number, and it's implicit in what they did that these three timescales are all the same, the nonlinear, the triple, and the spectral transfer. And then if you use the energy transfer rate as this model of the energy at that scale over the spectral transfer time, put those things in there, assume that you're in an inertial range where there's no direct forcing and there's only negligible dissipation, then you end up with, assuming that epsilon is a constant on that basis, you can rearrange here to give you the what's called the Kolmogorov spectrum. E of k, the spectrum, is k to the minus 5/3 with some dimensional stuff. Even though it doesn't appear in Kolmogorov's first papers, the 1941, since he worked in real space, not Fourier space. Nonetheless, it was completely equivalent to this when you switch to Fourier space. Okay, what does that have to do with MHD? So in 1965, Kraichnan had his MHD phenomenology, MHD turbulence, and the key thing that he did was this idea about epsilon, the energy transfer rate from energy that's moved from k's below the red line to k's above it, for all possible red lines in here, was that he made an assumption. He postulated that the energy transfer rate epsilon was directly proportional to the triple correlation timescale, arguing physically that since the triple correlation is what determines how long structures last and what destroys them, that's what governs the efficiency of the energy transfer. So that the energy transfer rate should be directly proportional to that time scale. Right, that's not quite enough though. It's not just that times a constant, that's not dimensionally correct. So if you argue further that that the epsilon should only depend on things that are local in Fourier space, so the wave number in the energy spectrum, then the unique prediction that you get is this one here. The epsilon is some order 1 constant times the triple correlation timescale times the spectrum squared times the fourth power of the wave number. I like to call this the 2, 3, 4 rule because of the powers and subscripts there, just as a shorthand, but the physics is really this idea of Kraichnan's that the dissipation rate, or the energy transfer rate better, is directly proportional to the triple correlation time. Well, what is this triple correlation time though? Lots of things can cause decorrelation, just the nonlinear effects of the flow, the advection. So 1 over the nonlinear time is a rate of nonlinear decorrelation. And if the 1 over the triple time is the rate of decorrelations, so that's going to be equal. If we add up all of the possible rates, we should get the total decorrelation rate, the triple time. So 1 over the nonlinear time. What else could decorrelate? Waves are going to mess with phase coherence. So 1 over the wave period. There might be other things in here too, forcing, dissipation. We'll just focus on these two here. And in particular, for the MHD case, Kraichnan argued that if the waves are high frequency, meaning that the wave period is much shorter than the nonlinear timescale, effectively, you can forget about this term here. That becomes small compared to the other one, and you get that the triple time is effectively the same as the Alfvén wave timescale. And that's what Kraichnan did. He took that approximation, put it in here. We'll see that in the next page. For 3D MHD. All right, so his starting point was incompressible MHD, 3 dimensions with a strong mean magnetic field. I'm going to write B naught as a uniform magnetic field in the Z hat direction. And as we mentioned before, strong just means that the mean field amplitude is much greater than the fluctuation amplitudes. Then you treat the fluctuations as Alfvén waves. And in that sense, it's really Kraichtnan's phenomenology. We often think of it, or used to think of it, as being a theory of strong turbulence. But now we know that it's really a weak turbulence situation because the nonlinear time is very very long compared to the wave time scale. And so the nonlinear effects are perturbative in that sense. But the key next step in Kraichnan's approach was that, yes, you have the wave, Alfvén wave frequency, k dot b naught, and 1 over that gives you the Alfvén time scale. But he argued that you can just approximate that as k times b naught, ignoring any anisotropy associated with that time scale there. Okay, so why? We'll sort of talk about that shortly. So if you take that wave time scale, approximate it as isotropic, substitute it into this 2, 3, 4 rule for the energy transfer rate, then the tau3 becomes a 1 over k b naught. You've still got the square of the spectrum and the 4th power of k. Assume epsilon is constant again, meaning independent of k. Rearrange and you get that the Iroshnikov-Kraichnan energy spectrum is some numbers, some factors times k to the -3 halves. Okay, so that's more or less what Kraichnan did. Iroshnikov got the spectrum in a couple of different ways. One of them was very similar to this approach here. The other was a diffusion model of the cascade process. Yeah, but as I keep hinting at, I mean, there's a problem, right? K dot b naught approximated as k times b naught. That'll be fine as long as k isn't nearly perpendicular to the mean magnetic field. When it is, things are going to be rather different. Does that change things? Is there much energy associated with modes with k nearly perpendicular to b naught? Just as a side comment here, are there situations in which you could have a wave time scale that was approximately isotropic? Even in MHD, there probably is, although it might be hard to realize it. If you only had fast mode waves, roughly their dispersion relation is isotropic. So you could plug that and the fast mode dispersion relation or an approximation to it, isotropic approximation to it in here, and you would get a k to the -3 halves spectrum in that case. So if you could have weak, fast MHD mode turbulence, it should have an Iroshnikov-Kraichnan spectrum on the basis of these arguments at least. Okay, and related to all of this about the isotropy and anisotropy is that this formula, the 2, 3, 4 law, how do we get it? Well, we assumed completely reasonably that the energy transfer rate is proportional to the triple correlation or decorrelation time, and then use dimensional analysis to get the rest of the factors. That will only work if there's no distinction between different components of the wave vector, right? So k and k perp and k parallel, they're all kind of the same in this mix here, so we just have a k. That will be good if things are isotropic. If they're not, though, then you would have to multiply this by some unknown function of, say, k parallel over k. And that would make things a lot more complicated. Right? And in particular, you'd have this undetermined function over here, and you wouldn't be able to say exactly what the spectrum looked like since it would involve that unknown function. Not what we want, so you can see why approximations of isotropy were made there. Okay, so just emphasizing that again, here's a system, thinking of it as a simulation cube with a mean magnetic field, strong mean magnetic field threading through it. There's a preferred direction because of that, and you would expect things to look a bit different along the field compared to across the field, especially if that field is energetically strong. However, maybe there's some wiggle room here, right? Suppose I choose a system and the initial conditions are chosen in such a way that if I take 1 over the Alfvén timescale, excuse me, which should be k b naught times the cosine of theta, if I choose my initial fluctuation so that cosine theta is pretty much 1 for all of the fluctuations. So this KB0 is a good approximation. Initially, does it remain a good approximation? What does the dynamics do to the fluctuations? Do they stay having this sort of behavior, or does the anisotropy come in and the cos theta factor make a difference? And the answer is it does not remain a good approximation. The dynamics does not want you to stay with KB0 being approximately tau A. The cos theta is there. And the reason really is that you get an immediate excitation of 2D modes, even though they weren't present initially in this situation. And once you have 2D modes there, then they combine with the other modes to drive a transfer of energy to smaller and smaller perpendicular scales. So that's what the next few slides are about, how we explain that geometrically and mathematically. Yeah, and there's been a lot of work on this. There are some of the papers there, and not all of them have been looking at it from this way of the absence or presence of the 2D modes, but that's some of the ideas there. All right, so as an explanation, there's really 2 steps to it. If we look at the geometry of the situation over here, the mean magnetic field B0 is going across the page. K parallel then is the wave component of the wave vector in that direction, and K perp is up the page here. So these red arrows are supposed to indicate the wave vectors associated with some Alfvén waves. One of them, this one going to the right, propagating to the right, and the other one propagating to the left. Okay, now the way I've drawn them is not a coincidence here. They exactly cancel in terms of their parallel wave vectors. One is plus, the other's minus, so they add up to 0. So the net effect of this right-going wave interacting with this left-going wave is that they produce a mode, if you like, a Fourier mode, not a wave, but a Fourier mode that has no K parallel. So you might call that a 2D mode. It's only got structure across the field. This green line here. And if you choose your initial conditions, so that the red ones, the waves have a lot of different K parallels and different K perps, there's a lot of structure, a broadband in K, then you're going to get a lot of structure in your 2D modes that you generate too. Broadband set of 2D, two-dimensional velocity and magnetic modes. Okay, so even if you didn't have any 2D modes to start with, you generate them like this. And once you do have them, then they can couple, right? So we take that 2D mode here and we add it to another red mode, red plus green, propagating mode plus a 2D mode drives another propagating mode, Alfvén mode. Notice that because we're adding a 2D mode, it has the same K parallel as the driver mode. Okay, so the transfer is all in the K perp direction. We're moving energy from this light red to this dark red, so that's to larger K perp, transfer to smaller perpendicular scales. And whether that happens or not doesn't depend on the amplitude of this 2D mode. Okay, all you need is it just has to have some energy in it. Okay, the amplitude is important because it controls the efficiency of the process or how fast it's all happening. But in order for it to happen at all, perpendicular transfer, you just need any low level of 2D stuff there. That's the geometric picture of how it works. We'll just run kind of zoomed out. It's how it works mathematically using the Elsasser variables on the next slide. So and just as a reminder, those are Z plus or minus, is V plus or minus B, B the velocity fluctuation, B the magnetic fluctuation in the right units, velocity units, say the Alfvén units there. So if we start with 2 Elsasser modes, and this shaky looking sketch here. We've got the magnetic field, mean magnetic field along the paper in the horizontal direction. In the same plane as the paper, we've got a Z plus fluctuation, and out of the paper, we've got a Z minus fluctuation. Now, because these have to be solenoidal, the wave vectors associated with those have to be in particular directions too, right? So they have to be perpendicular. The wave vector of the Z plus has to be perpendicular to it, and the Z minus perpendicular to it. So that plays out along these lines here. So Z plus, because it's in the X direction, P is the plus amplitude, P for plus. In the X hat direction, nothing in the Y and Z, where B naught is the Z. The wave vector for that mode has a component in the Y direction, so this way, and a component along the field. And then the Fourier mode structure is e to the I, nothing in the X direction, K plus Y plus K parallel Z. Z minus, however, is polarized differently. It's in the Y direction, okay, M for minus, and so its K vector can be in the X direction and the Z direction. And we choose the component in the X direction to be whatever it is, arbitrary. But in the Z direction, we specify that this is a minus sign here, so that these two, when we add them, will give us a zero. Right? We want the two modes to be counter-propagating such that they can produce a 2D mode. So we're looking at that special case. And then the Fourier structure here is K minus X plus 0, and that should be a minus sign there, K parallel Z. Okay, and then you really just follow your nose. You've got these two Alsacer modes, Z plus and Z minus, polarized in this particular way with their wave vectors. You substitute them into the Alsacer version of the MHD equations. You use the fact that they're solenoidal. That enables you to determine the pressure for each wave vector. And it turns out to be convenient when we get the solutions to have this parameter involving the transverse wave numbers. Right, K plus and K minus are the transverse wave numbers for the two plus and minus Alsacer modes. So their product over the sum of their squares, which is always less than 1, turns out to play a role in this in the solution here. Okay, so follow our nose, it's dot, dot, dot. We skip the details and you get that the time evolution of the Z plus when it's a 2D mode, right? So now the K parallel is exactly 0, but the perpendicular structure is in the X and the Y directions, is I times the amplitude of the two modes, the plus times the minus, just a little off the screen maybe there, times this vector, X hat, Y hat, Z hat, nothing in the Z hat direction because we're driving a 2D mode with some perpendicular Fourier structure, K minus X plus K plus Y. And a similar thing for the time evolution of the Z minus 2D mode, okay? Same K minus K plus, but the vector is a bit different, okay? So the polarization amplitudes in the X and the Y directions are a little different. Just a reminder what alpha is there. Okay, but we remember that the Alsacer variables are just V plus magnetic fluctuation or V minus it. So if we add and subtract these equations here, we can get the evolution for the 2D magnetic fluctuation and the 2D velocity fluctuation. Fine. You get some factors in here, the Fourier structure and the product of the amplitudes, and then two vectors that give you how much excitation there is in the X direction and the Y direction. And in general, those aren't 0. But that's really the point. So the time derivative of the 2D Fourier mode is generated by these counter-propagating Alfvén waves is essentially K plus in the X and K minus in the Y direction. As long as this transverse structure, that is those K plus and K minus aren't 0, you're going to have a non-zero time derivative for the magnetic 2D fluctuation. So you're going to generate some or enhance whatever's there. Same thing for the 2D velocity fluctuation. The vector's a bit different, but in general, it's not zero. What you can say, though, is that if K minus was equal to K plus, that would mean that alpha was equal to a half as well, and that piece would be exactly zero, and so would this. So in that case, that special case where K minus is K plus, or the negative, then you don't drive the ddt of the V2D is zero, exactly zero. So you don't generate any velocity, 2D velocity fluctuations in that special case. But that's not most situations. Okay, that special case has been looked at before. Vasquez, for example, and Holweg, and Hausen, Nielsen. And I'm a bit surprised that this result for the general case hasn't appeared somewhere. Maybe one of you can point me to where it is, if it's out there. But the point really is that you're always, in general, you're going to generate some magnetic and kinetic 2D fluctuations.
I'm a bit confused. This equal to zero, you said V2D dot is zero when K plus equal to K minus. But there's alpha sitting there. So is alpha half or?
Yes, yes. So here's alpha here.
Oh, I see. Okay, alpha is okay. I see.
The same, then it works out to be a half. Yeah.
I see. Okay, great.
Yeah, it's not completely obvious. I agree. What was I saying here? Right. So because of that alpha and it being less than 1, typically, meaning almost always, I think, you're going to generate more magnetic energy in the 2D modes than you get kinetic energy in the 2D modes. Okay, so in other words, the alphane ratio, the V squared over the B squared, just for the 2D modes that you generate this way, is going to be less than 1 typically, which is interesting. It has some relevance to the solar wind, for example. Okay, so that plays out like that. You generate some 2D stuff, provided you have cancelling K parallels in some of your alphanic fluctuations, propagating fluctuations. Right. That was all really just, though, for the case of you start with 2 fluctuations, one going left and one going right. What do you generate? We can look at an ensemble of fluctuations with a simulation where we have a whole lot of broadband initial conditions. So that the simulation study here, we've got 3D MHD in the spectral code, unforced, and we look at 2 cases, one with no mean field, B naught is 0, and the other with a very strong mean field, 5, meaning that there's 5 squared or 25 times as much energy in the mean field as there is in the fluctuations. And since we're trying to show that see whether the Iroshnikov-Kraichnan phenomenologies pan out, even though there is this anisotropy-isotropy tension, we choose initial conditions that are favorable to the Iroshnikov and Kraichnan approaches. Okay, and in this case, that means here's K parallel on the horizontal and K perp on the vertical. The 2 red circles, quarter circles, the annulus between those is where all our wave vectors have to lie. Okay, the modulus of K has to lie between 10 and 32, reasonably large values there. But that's not all. Since we want it to be IK appropriate, we also restrict the parallel wave number to be between 10 and 20. Okay, so that means it's got to be in this blue box here. So the only fluctuations we have in the simulation that have energy in them are the intersection of this blue box and the annulus. Okay. In particular, we don't have anything on this axis, the K parallel equals 0 axis. No, there are no 2D modes because all our K parallels are at least a third of the total K. So K parallel B naught is approximately K B naught, to within a factor of 2 or 3. And we've got high frequency propagating waves because B naught is largest at the value of 5. there's a lot of Ks in this range, a lot of different wave vectors. So we have a broadband set of initial fluctuations. And then the other aspect I want to talk about here is the polarization. You still have a choice about how you want to excite the fluctuation. So if we have B0 here on the horizontal axis and the black axes are in the plane of the paper, and K is in that plane, the wave vector is in that plane. The alphanic or toroidal fluctuations are those that are out of the plane. So this is the direction of the amplitude of linear Alfvén wave fluctuations. And the other one, the green, which is in the plane of the paper, called poloidal, that would be in the incompressible case, the limit of the slow mode fluctuations. They're not slow mode since we're incompressible, but think of them as kind of slow mode like, I guess, in terms of their polarization properties there. So in the simulations, we're going to focus mostly on exciting toroidal or alphanic fluctuations, since that's what Kraichnan was using in his phenomenology, that you had Alfvén waves there. We're not going to insist that they have the exact eigenstructure of Alfvén waves. The V doesn't have to be exactly plus or minus B, that can be an arbitrary ratio, but the polarization is in this blue out of the K cross B plane. Okay, so there's a few plots to look at to help us understand what's going on across the different sorts of runs. Most of them are going to be energy spectra, two-dimensional ones, where it's E of K parallel and K perp, and look at contour plots and then sometimes some surface plots just to emphasize some features. And then I think I'll get on to the Alfvén ratio, which is the kinetic energy over the magnetic energy in the incompressible case, as a function of the K perp and the K parallel as well. Just reminding you again, if the fluctuations were essentially Alfvén waves, then you would expect an equipartition of the kinetic energy V squared on the top and the magnetic energy B squared on the bottom. So you would have an Alfvén ratio of about 1 in that case. So just before we look at the dynamics, this is almost the initial condition, right? T is 0.005, so it's only a few time steps after the start. And KZ on this axis here, heading to the right, and KX as a proxy for K perp, and one heading off to the left. And this is the log of the total energy in the fluctuations at these wave vectors. And log scale here, -2 down to -10. You can see that if we look between K perp, KZ equals 10 and 20, or mod KZ equals that, you get these two blocks, right? That's where all of the energy was initially, because we zeroed out this stuff in here. We didn't want anything there because that is not favorable to the Iroshnikov and Kraichnan phenomenology. So we start with effectively these two blocks, but even after this tiny time, we've generated some stuff in between and a bit of stuff out. There's been some spectral transfer to these larger K parallels and larger K perps, and in particular, you can see that the place where there's been the most of that spectral transfer is into the 2D modes. There's a slight ridge there, and there's definitely a bit of a hump as you go through the middle there. So we're putting energy into the 2D modes immediately with the dynamics. Right. So this is the same sort of thing, but just done as contour plots. We're looking at the log of the energy as a function of the parallel wave number and a perpendicular wave number for two cases. One where there's no mean magnetic field, and those are the blue contours here. They're a bit extended in the K parallel direction, which I need to understand a bit better. I don't have a good explanation for why it's spread quite that much in the parallel. These dotted or dashed brown curves are the spheres. So if things really were isotropic, you would expect the contours to be parallel to them. and are not. But what should we take away from this plot? That we have had a lot of spectral transfer in the perpendicular direction and in the parallel direction. Okay, so the energy is spreading out very roughly, isotropically through Fourier space when there's no mean magnetic field, and we didn't have any 2D modes in the initial conditions. The other case, the case on the right here, same stuff, log of the total energy at some later time in the simulation. These blocks here are the initially excited regions, and there's still a lot of energy in those two blocks. But you can see that the blue curves don't look at all like the ones on the left. Okay, they've kind of focused and running up the page. So because there's been a little bit of perpendicular transfer and really not much parallel transfer at all. Right? If we look at this contour here, it's labeled -10, 10 to the -10, and it doesn't even get out to kz equals 50, whereas on this one over here, where there was no mean field, the -10 is out past 80 and even 100 in the perpendicular direction. Okay, so much weaker transfer in the parallel direction here, and that's really what we were expecting based on our analysis. Once you have 2D modes, which when you have a strong B0, they get excited straight away, you turn off the parallel transfer. That's the right way to say it. It's not really that you enhance the perpendicular transfer, it's that you suppress the parallel transfer. And that's what we're seeing in there. Okay, now this is a very busy plot. Please ignore the right-hand plots, the two rightmost ones. What we want to look at really is each row is a different mean magnetic field value. So the top row is B0 equals 0, and the bottom row is B0 equals 5, the strong case. And these are effectively, again, the IC. So it's like this plot here, just done a bit differently. And so we've got a contour plot for here. Unfortunately, KZ is on the vertical this time instead of the horizontal. So that's the parallel direction. And you can see at this early time, there's not much difference between these two. Be hard pressed to say there was much on the way there. B0 equals 5 on the bottom, 0 on the top. And if you take cuts through them, which is what this row column here is, so choose a KZ, say 5, and do a cut through there, and then plot that as that light blue curve here. KZ equals 5 is the light blue. That's what a cut through the two-dimensional spectrum would look like there. So this is just E as a function of K perp at this K parallel. And you can see in both cases, B0 equals 0 and 5, the cuts are dominated by this green one, which is K's equals 15. That's right in the middle of the initial conditions, so not much has changed, especially as we're so early. But we have generated a little bit of dark blue, which is the 2D mode. Not quite as much in the K parallel equals 5, and the large K parallel, which would be out here somewhere, is off the scale on this. There is some there, but it's too small to see on this plot here. Right, so that's orientation, what the initial conditions and very shortly afterwards look like. Not much difference between the two cases. What happens if we roll the time on, do some dynamics? Do they stay looking the same? Which would be arguments in favor of isotropy being a good approximation, or are they different? So here they are. Again, just looking at this left-hand column, B0 equals 0 on the top, 5 on the bottom, very different plots. A lot of spread in both directions for the no mean field case, hardly any spread in the parallel direction for the strong mean field case, and some spread in the perpendicular. A little bit easier to see perhaps on the second column. So the green, remember, is what was the initial condition K's equals 15, or in the heart of the initial conditions, is better to say. And you can see it's still strong and dominating when you've got it in the mean field case. The other ones are there. There's a bit of 2D, but a factor of 100 at least less than the initial condition level. K's equals 5, smaller still. And the red just visible down here at very large Kz equals 40, about here, a cut through about there. However, what you can see is that at the larger K perps where there is energy, there's not a whole lot of difference. Okay, it's a log scale, so it's more than you think, but the slopes and the behavior is pretty similar for each of these K perps. Okay, the different colored curves are all kind of doing the same thing here. Same is true in the no mean field case at the larger K perps, but at the low values of K perp, there are some significant magnitude differences in these things here. This third column is really, again, the same data just viewed as a surface plot rather than a contour or a cuts plot. And you can see the spreading to give you this sort of ball dress structure, and the essentially only perpendicular spreading when there's a strong mean magnetic field. I should say too that these aren't enormous simulations. They're 512 cubed or maybe 1,000 cubed sometimes. But because our initial conditions are starting in this K equals 10 to 30 range, that's a factor of 10 smaller in effect. So the Reynolds numbers that you can get to out of this aren't great. And there's quite a bit of dissipation already happening at these sorts of times. It's a numerically difficult thing to achieve, to have the high K initial conditions and still have a good Reynolds number. But that's what we've got to deal with. Okay, that's enough about that. So that was all for the case where the initial fluctuations were polarized like alpha waves. The favorable situation for Kraichnan and Iroshnikov. What about if we relax that a bit and say, well, okay, I don't care how they're polarized. Let's polarize them randomly. Some colloidal, some alphanic. Does that change things? And the answer is not really. So here again, this is the contour plot with K parallel on the horizontal, K perp on the vertical. No mean field case, somewhat spherical contours, the blue ones, a bit overextended in the parallel. And then the strong mean field case, a bit more evident that there's been some strong perpendicular transfer. That extra polarization is helping you. There's some extra energy available to generate 2D modes. And so you're sort of heading towards more normal, if you like, standard simulations where you don't make any restrictions on what the fluctuation geometry looks like. Right, and then this third example really highlights that. So what we have here is that these are both B naught equals 5 simulations. The one on the left is one of the ones that we've already looked at. So there's no 2D modes in the initial conditions. The K parallel is restricted to be between 10 and 20 magnitude. And then the other case on the right is there's no such restriction. All we do is we say that the magnitude of the wave number has to be between these two limits. So we're in that annulus, and that's it. There's no box to fit into as well. We're just somewhere in that annulus of magnitudes between 10 and 32. And a striking distance here, right? These are the same time, much more extended perpendicular transfer of energy, and still very weak parallel transfer. It's the same kind of thing here, right? Things are just creeping out to about 50 or minus 50 in the parallel direction, but the perpendicular transfer has been stronger here. Why is that? Well, it's because you had these 2D modes present in the initial conditions with amplitudes that are comparable to all the other modes. Here, you had to generate the 2D modes first. That's quick, but the amplitude that you get out of those modes is low. And that amplitude determines how efficient the perpendicular transfer is. So here, yes, you generate 2D modes, but their amplitude is so low that the process of perpendicular transfer is weak. Here, it's strong because the amplitude is strong. Okay, not sure exactly how I'm doing for time there, but that's all I wanted to say really on that side of things. Just to summarize, when you have incompressible MHD, if you have a whole lot of fluctuations with different K-parallels, and there's a strong mean field, then a lot of those K-parallels are going to be high frequency waves. Okay, the omega K-parallel times the Alfvén speed is going to be large, and that's going to be the dominant decorrelation effect in the let's call it turbulence, weak turbulence. Because of that, you generate some 2D modes, and then the subsequent dynamics isn't really going to behave like the isotropic Iroshnikov-Kraichnan approaches then. So we've said that. And so I think it's going to be hard to see a k to the -3/2 spectrum because of the isotropic Iroshnikov-Kraichnan arguments, at least. There are other reasons that you might see a k to the -3/2. You know, the Moldy-Rev and Cousins approach to MHD turbulence, they get a k to the -3/2 prediction, but that's for a very different reason. It's not related to the Iroshnikov and Kraichnan at all. It's kind of a unfortunate coincidence for the outsider that they both say 3/2, even though they're independent and distinct models for why that is the same exponent. And I haven't shown anything here, but if you do simulations with compressible, specifically polytropic MHD, you see the same sort of behavior as well. So yeah, the k to the 3/2, -3/2 is a difficult thing to argue for using Kraichnan and Iroshnikov isotropy assumptions. Okay, having said all that, let me just mention what's essentially some history here, I guess. What Iroshnikov and Kraichnan actually did isn't what I said Kraichnan did earlier in the talk. So we have this table here of some various features and what each of those guys assumed. Start with Iroshnikov. He looked not at incompressible, but at compressible MHD. He did have a uniform magnetic field that was strong. And that was in contrast to what Kraichnan did. Kraichnan looked only at incompressible. He did not have a uniform B0, even though I kind of suggested that he did earlier in the talk. What he had instead was a randomly oriented, dynamic, large-scale magnetic field that was strong, energetically strong, but not uniform. Right, so and because it was randomly oriented, you argue that it's isotropic, and depending on where you are, because you're averaging over all this stuff, the approximation about k dot B0 being the same as k B0 works out to be okay, because the large scale field is so random. Okay. Implicit in that is that there's some sort of scale gap between the large scale random field and the smaller scale fluctuations, right? The large scale field was maybe on scale 1. The fluctuations are on scale 1/10 or 100th, much smaller than the large scale. Not quantified, but present in the discussion in the paper there. Other differences between the models. So Kraichnan specifically assumed that the fluctuations were Alfvén waves. It's a weak turbulence approach. So you you argue that at leading order they're Alfvén waves, and then nonlinear corrections give you this k to the -3/2 spectrum in the end, after you assume that the dispersion relation is approximated as isotropic, even though it is clearly anisotropic. Did Iroshnikov do the same thing? I'm not really sure. I mean, he has a section where he shows that the Alfvén wave contributions should be small. And he says, this is a direct quote here, energy flow through eddies is governed chiefly by the compressibility. And then he goes on and he does more calculations and stuff. I can't tell whether the calculations that he does after that are supposed to apply to the fast and slow MHD modes, or whether they're still applying to the Alfvén modes. Maybe I need to learn some Russian and read the original, or maybe it's just not clear in the paper there. In any case, it's still a weak turbulence approach. You're using the fact that the nonlinear time is much slower than the wave periods to get your results there. And in the end, he averages over directions of the dispersion relations effectively to get the same answer, k to the -3/2. So it's interesting that there are some quite strong differences in compressible versus compressible, uniform mean field or not, but they both came up with the same form for the spectrum. And then for completeness, we should mention some more modern phenomenology approaches for MHD. The original Goldreich and Schroeder critical balance model assumed that you had incompressible 3D MHD. You did have a uniform B0 in it, but it wasn't strong in the usual sense. The fluctuations, the delta B, the amplitude of the magnetic fluctuations, was assumed to be of order the mean field strength. Okay, so equipartition of energy between the fluctuations and the mean field. So you can view that as sort of a random large scale B as well. So they're both there. What are the fluctuations in that model? They're generically toroidal, which doesn't impose wave properties, but wave properties are used, in particular the wave timescale. The Alfvén timescale is a crucial element of the critical balance approach. So there's lots more to say about comparing these things and other aspects of turbulence in the MHD context. There's a review by Bill Matthews and myself that came out last year. There's a lot of pages in it, so maybe too many to be reading the whole thing, but there might be some sections in there that clarify some of these points. Right, so that was just an aside. I want to, in the last couple of minutes here, I think, say a few things about the Alfvén ratio, kinetic energy over magnetic energy for the fluctuations, and particularly how it connects what its value in the solar wind can tell us about the nature of the MHD scale fluctuations in the solar wind. So Iroshnikov and Kraichnan phenomenologies, and indeed any weak turbulence phenomenology for MHD, predict that V squared over B squared will be about 1, because the average kinetic and magnetic energies are the same for Alfvén waves. That's not what you see in the solar wind. When you look at MHD scales, you typically get a value of about 1/2. So what's going on? They can't really be Alfvén waves. On the other hand, we observe a lot of Alfvén waves in the solar wind. So we've got waves there a lot of the time, but not enough of the time to give us a volume average of 1 for this Alfvén ratio. We get much less than that. Something to understand there. And if we do simulations, MHD simulations, compressible or incompressible, then can you get an Alfvén ratio for the whole domain of about 1/2? You can, but you have to bias things in your favor there. You've got to put a lot of the initial energy or the driving energy, in 2D fluctuations. So that you end up with the 2D component of the fluctuations being energetically dominant, something like 80%, to get this value, observed value of RA, L-Fane ratio of a half. Interestingly, if you treat the solar wind fluctuations as a composite collection of stuff, some slab L-Fane waves and some 2D modes. Kind of a ridiculous model, really. I mean, just using my hands here, what you're really saying is that Fourier space, which should be a full three-dimensional volume, can be divided up into this 2D plane of the 2D fluctuations. All of the 2D energy is in that plane. And then this line, the K parallel axis, is where the energy of the L-Fane waves lives. All of the rest of the space you're arguing is empty. Nobody really believes that's true, of course. But as a stick figure model, skeletal model of what's going on, it has some advantages. It's pretty easy to work with, and you can do things like this Bieber et al. Test here to see what that would indicate. And you get the same value. If that was the situation in the solar wind, 2D and slab, nothing else, then the best fit out of that is that 80% of the energy is in the 2D modes and only 20% in the slab L-Fane wave modes. That's a 1 AU. That was the first time that approach was used. Since then, over the next 20 odd years, there have been a lot of studies at different distances, other scales than just the ones that were used in the original Bieber case, and they all give comparable results. Sometimes it's a bit higher, sometimes it's a bit lower, but it's always mostly 2D. Most of the energy has to be in 2Ds if it's a slab plus 2D model. Okay, and there's some details in various review papers. Okay, so we can do some simulations to try and tie this down a bit better. Typically at 1 AU in the solar wind, the RMS magnetic fluctuation over the mean field strength is about a half. The sound speed and the L-Fane speed aren't too different, 50 or 60 kilometers a second. So the plasma beta there is something like 1. Most of the time, there's a lot of scatter. The RMS velocity, the delta V, is something like velocity fluctuation, that should say, something like 20 or 30 kilometers a second. So normalizing that by the sound speed gives you the Mach number, which is something like a half in that case. So if we try and use these parameters in our simulations and see what we get for the L-Fane ratios that come out of them, we might be able to say, constrain what the solar wind fluctuations are, or at least a suggestion in that direction there. And something to note there is that there's not really any case for using a dominant magnetic field in the solar wind, at least around these sorts of distances, because delta B over B naught is not a tiny number, it's a half. Right? Basically, delta B and B naught are of comparable magnitude. This isn't 1 over 20 or anything. Okay, so I'm going to show you several plots like this, and this is just one isolated so that we can understand what's going on. So this is the L-Fane ratio on the vertical scale here, plotted as a function of plasma beta for a whole lot of simulations. So if we just look at these black crosses on the top to start with, these are all for the same sorts of initial conditions, in this case toroidal, meaning like L-Fane waves, polarized in the same sense as linear L-Fane waves. At high plasma beta, then we get a total L-Fane ratio of something like 0.8 or 0.8, 0.85, and it's pretty flat, doesn't depend much on plasma beta until you get down there towards beta is order 1. Okay, so this is large plasma beta is where the sound speed is faster than the L-Fane speed, and you're in some sense more hydrodynamic-like. As you go to lower beta, the total L-Fane ratio jumps up to be pretty much 1, kind of the Alfvén wave expectation. Okay, and again, it stays flattish as beta gets a bit smaller. What are these other curves then, though? So the black one is the total from all of the fluctuations, everything in your simulation. What do you get for the Alfvén ratio? If you can separate out just the 2D modes, you'll get this bottom curve, these green triangles here. Again, it's flattish, but it's definitely less than 1. It's hovering around 0.6 or so, roughly, very roughly, independent of plasma beta. Unfortunately, it's difficult to extract just the 2D piece from the solar wind observations. So really what you have observationally is only this total value. If you could also extract just the Alfvén polarized piece, maybe you have a better chance of doing that, then but you still need to know the wave vector. It's not easy. Then you'd get something in between. Okay, it's closer to the total piece, whereas the 2D one is not an outlier, but significantly lower than the other two there. Okay, so on the next page, I'm going to show the same style of plot with these 3 sorts of Alfvén ratio. Really, we only have to look at the total one, though, the top one, the black one, for different sorts of initial conditions. Right, this one was just those polarized like Alfvén waves. Here it is again here on the left. This is no preference to the polarization. So we have poloidal and toroidal, or Alfvén wave and pseudo Alfvén wave polarizations equally excited. And yeah, comparing that with solar wind observations, where we would expect, here's a half, which is what we observe for the Alfvén ratio. Nothing is in that range there for the isotropic initial conditions as a function of plasma beta. And the best one is this one here, down on the lower left. And that's when, as we were suggesting in the observational build-up there with the Bieber stuff, it's when you put 80% of your initial energy in the 2D modes. Okay, those with KZ equal to 0. And then the total and the 2D Alfvén ratios are all around the right level, 0.5, 0.6, pretty flat, independent of plasma beta. If you widen that a little bit, if you allow the 2D energy to be not just in KZ equal to 0, but in the neighboring planes, in the simulation sense, then it's a bit worse. The 2D stuff is pretty much the same, but the total is more like the Alfvén wave value of 1, heading towards it anyway. So if you want to use these sorts of initial conditions and match the solar wind observation, your only option really is to have either high plasma beta and some quasi 2D stuff, or any plasma beta and dominantly close to strict 2D, okay, fluctuations here. So the Alfvén ratio is kind of a probe for what might be going on with the solar wind fluctuations. Obviously, it's more complicated than just that one parameter, but it's hard to get agreement for generic initial conditions. You have to have some special types of fluctuations that persist. That's really the point. It's not that they're initial conditions. It's that these toroidal ones dominantly stay toroidal. The isotropic, of course, are going to stay that way a bit. And the quasi 2D ones, you keep having a lot of energy in the quasi 2D as the system evolves. So all of that points to the sort of the byline on my talk title, which was the role and importance of two-dimensional modes in MHD turbulence. And whether you have a uniform magnetic field or just a strong large-scale magnetic field, robust large-scale magnetic field, the structure perpendicular to that is important for the dynamics and the properties of the turbulence. So I'll stop there. That's a good place to stop. Thank you.